It's a wonderful institution. It's my first time in Korea, and I'm having a great time getting to know the country and the wonderful people here. And TAC, thank you very much for inviting me. As he said, I'm going to give 3 talks, all on centered around or aiming at looking at knot groups, which are a classical tool for studying knots. They are, by definition, the fundamental group of the complement of a knot in 3-space or in the 3-sphere. I came to be interested in orderable groups about a dozen years ago when I had been working on a problem with braid groups and singular braids and maps from singular braid monoid into something called a group ring of braid groups. And in doing calculations in a ring, if you want to cancel multiplicatively, you have to make sure you're not canceling out zero divisors, because you can get a wrong answer. If AB equals AC, it may not be true that B equals C if A happens to be a zero divisor. If you try to verify that, you see you can get a fallacy. So I kept worrying about that, and I kept asking experts if the group ring of the braid groups had zero divisors or not, and nobody knew, even experts like Joan Berman and Vaughan Jones. And then actually it was Joan who said, well, there's this Frenchman who proved something strange about the braid groups, that they're left orderable. And so I looked into that, and it turns out that left orderable groups have no zero divisors in their group ring. So I was very happy to learn that. And then I studied a little bit more about orderable groups and got quite hooked. And I found that many groups that we're interested in as topologists actually are left orderable or have two-sided orderings. And so I've been working on that for quite a while now. And this is specializing, zeroing in on knot groups, which turn out all to be left orderable. Some of them have two-sided orderings, and I've been part of the project to understand that, and there's a lot of open questions which I'll come to. So I hope I can get a few of you interested in this topic and maybe contributing to it. So here's the outline. I'm going to give today's talk will be basically introduction to orderable groups. You can think of it as maybe a short course in orderable groups. And my second talk will be possibly a continuation of this, and then show why and other 3-manifold groups. Not all of them. I should probably say left ordering knot groups. They can't all be bi-ordered. But the third one will discuss some certain knot groups which are blessed with even stronger orderability properties. And I'm going to introduce fibered knots, and bi-orderable groups. I want to say bi-orderability. So this is the plan. So let's start out with number 1. We have a group I'll always use the letter G to indicate a group. And left order or left ordering of G is a strict total ordering. Let's say less than of its elements. So by that I mean every two members of the group are ordered one way or the other. If G and H belong to G, either G is less than H or H is less than G, unless G and H happen to be equal. And it's transitive. G less than H, H less than K implies G less than K. But it has another property satisfying G less than H implies FG less than FH. In other words, it's invariant under multiplication on the left. And of course, if you multiply this inequality by F inverse, you would imply this. So I'll just put in blue that's, you don't have to say that, but it implies the reverse too. So it's left invariant. Now, orderable groups is actually a classic subject, been around for more than 100 years. And in the beginning, mostly they looked at two-sided invariant orderings. And it wasn't until maybe 50 years ago that one-sided orderings were concentrated upon as being much more common. And it turns out that about half the community talk about right-ordered groups and half of them talk about left-ordered groups. Algebraists tend to talk about right-ordered groups because their operators act on the right. Analysts and topologists talk about left-ordered groups because their functions operate on the left. So I've switched. I started out talking right-ordered groups. Now I'm going to stick with left-ordered groups. Oh, you can't see that. Okay. So if is also invariant under right multiplication, I won't write out the equation. You know what that means. You put F in the right instead of the left for that. Then we'll call it a biorder. And if such an ordering exists, of course it may not, but if it does, we'll say that the group is left orderable or biorderable. I don't have to write that down. An alternative viewpoint is to consider, I'll call it P, the set of all G and G, such that G is bigger than the 1. And this is the identity. If we're in an abelian group, I might call it 0 instead of 1. And if we're in an additive group. So this is the so-called positive cone. of a left order. It satisfies a couple of properties. First of all, the product of any two things in P again belongs to P. In other words, it's a sub-semigroup. Let's check, why is that true? Suppose F and G belong to P, so F is bigger than 1 and G is bigger than 1. Well, multiply this on both sides by F. This implies FG is bigger than G, but by transitivity, since G is bigger than 1, that implies FG is bigger than 1, so FG belongs to P. Sort of trivial calculation. Okay. And the second property oh, I'm sorry. Thank you. So G bigger than 1, if I multiply, that implies this inequality. And then F being positive implies that, and then transitivity gives you, yeah. And of course, GF also belongs to P, but the same argument. And the second property is that the group G itself is a disjoint union of P and P inverse. Let me clean this up a little bit. Together with the identity. So this means disjoint union. You see, if it's easy to check, if G is bigger than the identity, then G inverse is less than the identity. Just multiply this inequality by G inverse. So everything is either in P or P inverse. P inverse is just the set of all inverses of things in P. Unless it's the identity. That's okay. So in other words, we have a sub-semigroup which together with the inverse sub-semigroup partitions G in this nice way. Conversely, if G is a group having a subset P satisfying 1 and 2, then G is left orderable. By defining F less than, right over here, F less than G, by definition, if and only if F inverse G belongs to P. And I'll leave it as an exercise. To verify that this relation is a strict total ordering and left invariant. Left invariance is pretty clear. If you multiply something on the left, they cancel here. So anyway. Okay, any questions so far? Yeah.
What do we need if we want to, if you want to show that G is biodrome?
Good question. So I was about to say that actually. Moreover, G is biorderable if and only if there exists P satisfying. In other words, a positive cone 1, 2 here, and 3, it's invariant under conjugation. G inverse P G belongs to P for all G and G. It's like the normal subgroup, but here is a normal sub-semigroup. And in fact, a left ordering is a biordering if and only if it's invariant under conjugation. If G is less than H, then G conjugated by any element is less than H conjugated by that same element. It's easy to see. Okay, any other questions? Okay, so it's good to have some examples. I knew I'd have to take off my jacket at some point. Well, the most basic example, I guess, would be the additive group of integers. But here we have to talk about addition rather than multiplication. So that's in fact biorderable. So this is the group of integers. Which is additive. This is biorderable. In fact, there are exactly two orderings. The usual one and the reverse. Orderings always come in pairs. If you take the reverse ordering, exchange less than with greater than, you get another ordering. So this has only exactly two orderings. And of course, any abelian group that's left orderable will be biorderable trivially. Let's look at z to the n. This is also biorderable. I could have taken the additive reals too. But let me point out one that's not. Let's look at R star, which is the real numbers minus 0, with multiplication. Okay, that's a very familiar group, but it is not orderable. Even though it has a natural ordering, you see as minus 1 squared is 1, right? But we'll see, so is not orderable in this sense, because we'll soon see verify that left orderable groups have no elements of finite order. This minus 1 is not the identity, but its square is the identity. So it has order 2. So we cannot give an ordering to this in the sense that I've defined. We've got to move over here because that's sort of a blind spot. Let's look at z squared. You can think of that as the set of all lattice points in the plane, if you like, but this is biorderable using the lexicographic ordering. So you order as words in a dictionary. You look at the first element. You say that mn is less than m prime n prime if and only if m is less than m prime or m equals m prime and n less than n prime. Maybe I should use a different symbol here than here. This is in the usual sense of ordering of the integers, and this is a new one. Maybe I use a fancy less than. But there are many more orderings. Let's look at the integer lattice. I could do this all day. I could take any line through the origin. Let's first look at a line that has irrational slope, so it won't touch any other lattice points other than the origin. And just declare that everything to one side of this is a positive cone. Positive cone. And you can verify that it's closed under addition, and it satisfies everything belongs to P or P inverse, which in this sense is minus P, or the identity, which is the zero element. So take a line of irrational slope declare P equal all points to one side. Whoop. So we see we have uncountably many possible different orderings of z squared. Or we can take a line with rational slope. Let's say this happens to have a rational slope, some point out here is on it. Then we have to declare the positive cone to be everything to one side plus everything on a half line. Okay, I won't write that down, but you can do that also with rational slopes. But then you have more choices, actually four choices. This side and that bit, this side and that bit, this side and this bit, or that bit. Okay, so this fairly simple group already has uncountably many biorders. And this is rather typical. The set of all orderings, actually there's a theorem of Peter Linnell that for left orderings, the set of all possible orderings is either finite or uncountable. There's never exactly countably many orderings. So, but that's, I'm not going to go there.
So today, for that theorem, today, do we need biorderability?
No, left orderability. There exist biorderable groups which have exactly countably many biorders. Biorders.
Okay.
Yeah.
So in case of
But uncountably many left orders. Yeah. That's a theorem of Buttsworth. Okay. Now, a much larger group which is left orderable is, look at the group of all functions from the reals to the reals which preserve order. So this is homeo plus of R, which is set of all orientation, or maybe I should say order preserving, homeomorphisms from R to R. By order preserving, I mean with respect to the usual ordering of the reals. This is left orderable. As follows. Well, let's take a dense subset of the reals, for example, the rationals, and order them in your favorite way. So let R1, R2, R3, an ordered set dense, countable, subset of R. Now, Any continuous functions that agree on all these points have to be identical, right? Because it's a dense subset. So if F and G belong to homeo and they're not equal, if they belong to this group, by the way, the group operation is composition of functions, not addition or multiplication in the range, but composition. Compose functions. I'll just put that down. Consider Ri equal to first in this sequence such that F of Ri is not equal to G of Ri. Since F and G are not equal as functions, there must be something, someplace where they're unequal in that dense set. And just take the first one and then declare F less than G if and only if at that particular point F of Ri is less than, in the usual sense, G at Ri. And I'll again leave as an exercise, verify that this is a left invariant ordering. There are a couple of things to check, and you use the fact that when you multiply on the left, the thing you're multiplying on the left is order preserving, so that helps a lot, right? If F is less than G, H of F will also be less than H of G, but you have to verify that that's also the first place that those guys disagree. And this group is in some sense universal, at least for countable groups. There's a classical theorem, which I won't prove, but I'll just state. If G is a countable, I'm going to use LO for left order from now on, just because I write it so often. Then there is an injective homomorphism G to homeo. Did I use parentheses? No. Homeo plus of R. In other words, this group contains all countable left-ordered groups in some sense. It's sometimes known as a dynamic realization. And there's a beautiful paper on this subject by Andres Navas, although it was known much before that, but he gets a lot of information out of this thing. You can actually build such an embedding using the ordering and then extending.
Great.
So order preserving.
Well, this doesn't have a canonical ordering, so, but yeah, there will exist an ordering of this such that this is order preserving. In fact, yeah.
What about uncountable group? For example, like linear groups?
Sorry?
Uncountable group case?
It's not true for uncountable groups. For example, you can get groups of, yeah, this is uncountable, but you can get even bigger cardinalities. I'm not sure if, let's say, something with the cardinality of the continuum, such a group will embed in here. I think not, but I'm not sure. I don't know about examples. This is a good question. Yeah, this has cardinality 2 to the aleph naught. But I don't know if every group with that cardinality embeds. Question?
This is number of orders have to do something like the number of injected orders. This is the
Louder.
number of orders of G.
Yes?
Has something to do with the number of injective embeddings of G.
No, I think there will always be an uncountable number of possibilities. If you look at the way it's constructed, you start out by embedding the group just as a set into the real line in an order preserving way, and then yeah, so there are uncountably many choices even at the beginning.
For example,
There will always be uncountably many such embeddings. Yeah. Yeah. Okay, so enough for examples. I'll get more examples later on, as, for example, knot groups, surface groups, and so on. But let's now look at some properties. Of orderable groups. Well, the first very basic one is that they are torsion free. Which means if G is not equal to 1, then G to the n is also not equal to 1 for all n. Well, let's just verify it for positive n, and then it would follow for negative n. The reason is clear. So assume G is bigger than the identity. Then multiply by G on the left. So this is left orderable, implies torsion free. Sorry, I'm making a bit of a mess here. LO implies torsion free. If G is bigger than 1, then G squared is bigger than G and bigger than 1. So G squared is bigger than 1. Similarly, G cubed bigger than 1, etc. You can formally set up an induction if you like. G to the n is bigger than 1 for all n. And similarly, if G is less than 1, then just reverse all these inequalities and you get the same story. So That proves it. So that shows that there are no, except for the trivial group of one element, there are no finite left-ordered groups. We're always talking about infinite groups here. And that also shows that R plus, which I commented on before, is not left-orderable. Multiplicative non-zero reals. Now, how much time do I have? A full hour or 50 minutes? What's the usual?
1 hour.
1 hour.
Do we need to go to the class or at 5?
We'll see. If we get thrown out earlier, that's okay too. Okay. So I got biorderable implies unique roots. That is, f to the n equals g to the n for n you see, this is a, if you replace g with the identity, this implies torsion free. It's a fancier property. It's a stronger property than, well, the reason is in a biordered group, if G is biordered, then we can multiply inequalities. That is, if f is less than g and f prime less than g prime, that implies f prime is less than g prime. I'll leave that as it's a trivial exercise, but you do need invariance on both sides. It's not true in general for left-ordered groups. Not true in general for LO groups. So let's prove this by contrapositive. If f and g are not equal, assume without loss of generality, assume f is less than g. Well, if f is not equal to g, then assume without loss that f is the smaller one. Then multiply this by itself. F squared less than g squared. Almost the same trick as before. F cubed, multiply it by this, and you get f cubed less than g cubed. F to the n less than g to the n. So powers will never become equal if f and g are unequal. Okay. Now, now I'd like to talk about group rings. I started the hour discussing why I at first got interested, because I was worried about zero divisors and group rings. So let's talk about group rings. And zero divisors. So let's consider, as usual, G a group. And suppose R is a ring. Not necessarily commutative, but with identity. I don't know if you really need an identity, but let's not try to be completely general. Then we define the group ring. RG. It's a set of all formal finite linear combinations, I equal 1 to k, say, of such expressions. Take a group element, give it a coefficient in the ring, and you look at all such linear combinations. Finite linear combination, formal linear combinations.
R sub I, G sub I.
Thank you. R sub I, G sub I. So that's what the set is. And the product, addition is sort of obvious. You add things with the same group element by adding their coefficients. And multiplication sum Ri Gi equal 1 to k multiplied by some Si Hi, or let's say J Hj, J equals 1 to L. Define that product to be, again, the sum over all I and j. You just multiply the ring elements in the same order and the group elements in the same order. Ri, Sj. So it's as if they were polynomials. Gi, Hj. So this is the product in the ring, this is the product in the group, and you add them all up over all the different i's and j's in this range. And that's a well-known construction in algebra, sort of blending a ring and a group together and forming a bigger one. For example, if G is the infinite cyclic group written multiplicatively, the generator, let's say X, then this is simply the polynomial ring with coefficients in R. So it generalizes polynomial rings. Let's look at an example, let's say with a, suppose G has an element of finite order, let's say order 5. Little g. But g to the 5th equals the identity. But lower powers do not, so order 5. So g squared, g cubed, g fourth are not the identity, but g fifth is. And let's take, I don't know, r to be the integers. And let's look at a product g minus 1 times, or let me write it, 1 minus g times 1 plus g squared plus g cubed plus g to the fourth. If you multiply this out, you see you get a lot of cancellation, right? You get 1 times g and minus g times 1, and they will cancel. And in fact, this ends up being 1 minus g to the fifth. All the other terms cancel. But, hey, g to the fifth is 1, so this is 0. So both of these guys are 0 divisors. So anytime you have torsion in a group, you will have 0 divisors in the group ring, at least for the ring equal to Z. There's a conjecture due to Kaplansky in the 40s. It's called the 0 divisor conjecture. If G is torsion free, and R has no 0 divisors, then RG has no 0 divisors. So this is due to Kaplansky, as I said, in something like 1948 or something like that. I was a little baby. I was alive, but not very alive. This is still an open question. Still open. However, there is a theorem that if G is left orderable, then the zero divisor conjecture is true for G. G and any R with as above. Meaning here, no 0 divisors for R. Yeah.
I want to go back to the definition of group ring.
Yeah.
You said it generalized polynomial ring, right?
Yeah.
So a polynomial ring case, the group is the lattice Zn, right?
Sorry?
For polynomial ring, actual polynomial ring,
Yeah.
the group is just Zn.
Yes, if you have multivariable. Yes.
And what about,
Isn't it not the case? I mean, we don't admit the negative powers, right?
oh, that's true. So if you start with Zn, that's Laurent polynomial.
Yeah, that's now polynomial, but something larger than that.
Yeah, that's true.
Oh, those Laurent polynomials. Yeah.
So the Zn gives you Laurent polynomial.
Right.
What about a polynomial ring? What's the group?
Well, it's actually a semigroup of the positive yeah.
That's what
And the non-negative integers. Right.
So what do you
That's true. It doesn't really generalize Well, it does. It generalized Laurent polynomial rings. Thanks. Good point. Yeah. So let me just end with a sketch of the proof of this. Okay. Do I have time, or should I just?
How long?
3 minutes.
Okay. Yeah.
Maybe 5. Okay. Oh, okay. Let's look at. I'll leave this equation here. So the proof is consider the product with, let's order the h's. The addition is abelian, right? So let's say h1 less than h2 up to hl in the given left ordering of G. And now consider a product GIHJ maximal in the ordering. Okay, there's some finite number of products here. Take the biggest one in the ordering. I claim that we have to have J equals 1 because GIH1 will be less than GIHJ if J is not equal to 1. Because HJ is bigger than H1, and therefore you get this by left invariance of the product, and that would contradict maximality. So
Are we choosing minimal?
huh?
Are we choosing minimal one?
Thank you. Minimal. Yeah. I'm getting tired. Yes. And now, if GIH1 cannot cancel with GI prime, H1 if I prime is different from I because we're in a group. They can't be equal unless GI equals GI prime. GI H1 equals GI prime. H1 implies GI equals GI prime. So, therefore, GI H1 survives any cancellation. So you can't get rid of that minimal term in the ordering. You also can't get rid of the maximal term by a similar argument. So You also have no exotic units, but I won't go there. Let's just close with that. Thanks very much.